Hello everybody, welcome to the Ultimate Physics channel. The topic of today's video is Millikan's oil drop experiment, determination of the electron charge and charge quantization. Joseph John Thomson, popularly known as J.J. Thomson, was the first one to measure the charge to mass ratio of the electrons. His investigations into the cathode rays led to the understanding that the cathode rays were indeed negatively charged particles that we now call the electrons. This discovery led several scientists into doing experiments to measure the charge of the electron. Robert A. Millikan was one of them, and he reported for the first time in 1911 an accurate measurement of the electron charge. Millikan performed the original experiment in 1907 at the University of Chicago. Millikan's oil drop experiment consisted of visually observing the motion of charged oil drops under the influence of electric and gravitational forces. The oil drops could either be uncharged or be positively or negatively charged. Millikan's experimental apparatus goes like this. The apparatus consists of an atomizer, which is used to spray oil drops. An illumination source illuminates the whole thing, and then a reversible DC power supply is used to charge two metallic plates between which the oil drops travel, and the polarity of these two metallic plates could be reversed, and a microscope is used to observe the oil drops. These oil drops could be manipulated using the electric field, and they could be observed for long hours in this experiment. Now, by observing the motion of the oil drops and by balancing the forces, one can determine the charge on the oil drop. That is the working principle of this experiment. Let us proceed to discuss the physics of this experiment using some equations. As the oil drops emerge from the nozzle of the atomizer, they could be charged sometimes due to the frictional forces. Millikan's experimental basis was to balance the electric force acting upward and the gravitational force acting downwards. The frictional force on the oil drop when it drops downward is given by let us call that FF is a vector equation minus B times V, where B is a constant given by Stoke's law. Now this is the expression for the frictional force acting on a drop. So we have an oil drop, and this frictional force is going to oppose its motion because it is having a negative sign. That means these drag forces always try to oppose the motion of an object, therefore they try to resist the velocity of the object. So it is acting upwards, that is the frictional force. Now the gravity due to the mass of the oil drop acts downwards, so that is mg. If m is the mass of the oil drop, the gravity is going to act downwards. And then obviously we are applying an electric field, and the electric field is going to be in such a way to balance this gravitational force, so that is going to act upwards. You can call that this also right side. Because of its downwards direction, it is also assuming a vector character. Now these are the forces basically, and of course there is another force, that is the buoyancy, that keeps the oil drop afloat, but that is too small compared to these other three forces, so we are ignoring the buoyancy effects in this discussion. So in this frictional force, the negative sign is due to the fact that the drag force always opposes the velocity. Generally, when an object moves in a medium such as the air, the drag force on the object is proportional to the square of the velocity. That equation is given by This is the equation. Here we can clearly see that here we are using a linear connection between the force and the velocity, but the actual drag force is for having a nonlinear connection between velocity and drag force. It is proportional to the square of the velocity in this case. Right. Here the constant of proportionality is the drag coefficient B. But this equation does not hold for small spherical objects in a viscous medium other than air, where Stoke's law should be used. According to Stoke's law, the force is linearly dependent on the velocity of the object, right, which is this equation. And Millikan showed that Stoke's law, when applied to small spheres, requires a correction due to the atomic nature of the medium, and he found out the appropriate correction. So that is an additional contribution from Millikan. The buoyancy on the oil drop is neglected for this calculation since it is very small compared to the drag. When the two forces, namely the upward electric force and the downward gravitational force, are equal, the oil drop can be held in rest between the plates. Since the velocity of the oil drop is zero under this condition, the frictional force also becomes equal to zero because the velocity is zero, and therefore the electric force effectively is equal to the gravitational force. So we can write the equation there for that. So effectively we can write an equation where we have the electric force and the frictional force on one side, that is balanced by the gravitational force. When V is equal to 0, in this equation, our Fe is equal to mg. Just I'm writing the scalar form here. And then we know that the electric force Fe is given by the charge on the object times the electric field. So we have an equation where QE is equal to mg. Now the charge on the oil drop can be found out using Q is equal to mg over E. Now this is the expression in which if you know the mass of the oil drop, you would get the charge on it, because rest E, the electric field in this case E, is equal to V over D. That is, we have metallic plates between which we apply a potential. The distance of separation between the two plates, let us say, is d, small d, let us say, and the potential difference in this case is V between the two plates. So the electric field is given by V over D. Now substituting that here, we can write Q is equal to mg d over V. So the only unknown in this equation now becomes the mass of the oil drop. Now mass is equal to density times volume. So if it is a spherical drop and let us say the density of the oil is rho, that is rho times 4 by 3 pi or cube. This is the volume of the spherical oil drop. Rho is its density, so we can compute the mass. Now in order to find out R, which is the radius of the oil drop, we have to use Stoke's law. According to Stoke's law, the constant B is equal to 6 pi eta R, where eta is the coefficient of viscosity is the radius of the spherical drop. Now continuing from here, our original equation QE minus BV is equal to mg. If the electric field is switched off, then this term goes to 0, so your gravitational force is balanced by the drag force, and according to Stoke's law, the oil drop would acquire a terminal velocity. Therefore, when E is equal to 0, V becomes equal to Vt, and the negative sign here indicates, of course, the direction is opposite to the direction of the gravitational force. Therefore, we can ignore that. So we write Vt is equal to mg over B. Of course, there we have got an expression from Stoke's law for the B. Right? So again here also a mass is involved, for which we have an equation here. So under this condition we can write, from this one we can write mass is equal to BVT over G. This is from here, and then of course we have a mass here, so we say that rho times 4 by 3 pi r cube is equal to BVT over G. Right. Now B can be substituted with 6 pi eta r. So continuing there, rho times 4 by 3 pi r cube is equal to 6 pi eta r Vt, the terminal velocity, over G. Now here this r cube becomes r squared by cancelling out this r here, and then the pi is the common factor here, and then this 4 can be written as 2, and here 6 can be written as 3 by dividing commonly by 2. And therefore we have now r squared on the left hand side, we retain it there, and then take this 3 to the right hand side, and then that becomes 9 eta Vt over 2 rho G, 2 rho G, and therefore R is equal to 3 square root of eta Vt over 2 rho G. This is the expression that has to be used for the radius of the spherical drop in this oil drop experiment. And once we know the radius, we can plug in that value here to get the mass of the oil drop by knowing already the density of the oil drop. And thereby if we get the mass, and using the mass in our original equation, the charge is equal to mg over E, and the charge is equal to mg d over V. So we can substitute after calculation of mass. Here we can substitute to get the charge on the oil drop. Thus Millikan was able to calculate charge on the oil drops in the oil drop experiment. If the polarity of the power supply was reversed in Millikan's experiment, and if he could adjust the voltage magnitude, the oil drop could be moved up and down at will. It was reported that he could observe a given oil drop for up to 6 hours in some cases, and that the charge on the oil drop changed several times from positive to negative and vice versa during this period. In this manner, Millikan was able to perform the now famous oil drop experiment on thousands of different oils, and he showed that there is a basic quantization of electric charge, and he found this quantum of charge to be equal to the electron charge, which is 1.602 into 10 power minus 19 coulombs. That is the currently accepted value for the charge of the electron. Of course, when we quote the charge of quantum, we say that this is just E. Q is equal to E. And when we refer to the charge of an electron, we say that is equal to minus E. So the quantum itself is just a positive amount of charge, which is 1.602 into 10 power minus 19 coulomb. And when we say that an electron has a charge of minus E, that means it is minus 1.602 into 10 power minus 19 coulomb. Thus, the charge on any oil drop in this experiment is Q is equal to N times E, where N is the quantum number. In teaching laboratories, Millikan's oil drop experiment is preferably carried out using micron-sized plastic balls instead of oil drops, so that the mass of the ball can be directly taken to calculate the charge on it instead of going through the radius and density calculation routes. Robert A. Millikan, born in 1868, had his early education at the Oberlin College and then at the Columbia University. He worked at the University of Chicago for several years, during which he performed the famous oil drop experiment. Later on, he moved to the California Institute of Technology, where he served as the de facto president for several years. He saw the Caltech becoming a leading research institution under his leadership. Apart from the oil drop experiment, Millikan also contributed significantly to the problem of Brownian motion, and he provided the confirmation of Einstein's photoelectric theory by measuring the Planck's constant using that experiment. During his later years, he studied cosmic rays, whose naming is credited to Millikan. He was also a prolific textbook author and a very passionate teacher. He received the 1926 Nobel Prize in Physics for his important contributions. That brings us to the end of this video. Hope to catch up with you on another interesting video soon. Until then, it's a bye from me. Thank you.